afternoon, everyone. On behalf of Energy Futures Lab, I would like to welcome you to our event this afternoon. My name is Sana Kore. I'm a professor of environmental engineering at Imperial College and co-director of EFL. We are absolutely delighted that so many of you can be here to join our discussion for the future of our electricity system. For those of you joining us for the first time today, I need to give you a short introduction of the Energy Futures Lab. We are one of 7 global institutes at Imperial College, established back in 2005 to address some of the world's major energy challenges, bringing together teams from across the college with different research backgrounds and to carry out high-impact multidisciplinary research. Today's event is not only the launch of this particular report, but also the launch of a new series of white papers that we are developing, aiming to leverage the vast experience of our community of researchers to provide you with timely, impartial, and academically rigorous assessments of key energy technologies and important energy issues. In the coming months, we will publish white papers on topics such as the safety and sustainability of lithium-ion batteries and on industrial decarbonisation. Today, we are bringing you new modelling work and analysis from our IDLES programme team, which is in a white paper that explores how we can transform our electricity system to achieve net zero greenhouse gas emissions by 2035. I will now hand over to my colleague, Professor Tim Green, my fellow Energy Futures Lab co-director and the principal investigator of the IDLES programme, to get us underway.
Good afternoon, everyone. In a moment, we're going to hear from Dr. Marco Onidi, who is the lead author of this white paper. But before we do that, I have a few bits of housekeeping to address. So first of all, this is a 1-hour event, and the format is a short presentation from Dr. Onidi, followed by a panel discussion, and I'll introduce the panelists a little later. There'll be an opportunity for you all to pitch questions to the panel via the Q&A feature of Teams. We're relatively short on time today, so we probably won't get around all of the questions, so it would be really helpful if you would like questions you'd particularly like us to address, and we will prioritise those in the discussion. The event is being recorded and we'll make it available on Energy Futures Lab's YouTube channel, and I encourage you to share the video with colleagues who weren't able to attend today. The white paper itself is available for download off the Energy Futures website, and we'll be sending out a link to that at the end of the event today. I'd encourage you to take a look at that. There's a lot more detail in that than we'll be able to cover in the relatively short presentation. But now we're going to move to that presentation for an overview of the paper's main findings and key conclusions, and I'm handing over now to Marco. Thank you, Marco.
Yeah, thank you very much, Tim. Good afternoon, everyone. I'm Marco Onidi. I'm one of the authors of this white paper, and I'm going to try to present the key findings of that if Microsoft Teams is merciful to me. Okay, so if anyone could just confirm that these slides look okay.
Looking good.
Okay, so yes, we've developed this white paper to try to provide a contribution to the debate on what the future electricity system should look like and how it should transition towards a low carbon or zero carbon generation and storage mix. So that's been developed as part of something that's called IDLES program. It's a cross-disciplinary research program across different departments at Imperial, all linked to various strands of low carbon energy research. I'll go through a little bit of a background, why we have decided to produce this white paper, what its key objectives are. So obviously we're all aware of the UK's commitment to bring its greenhouse gas emissions to net zero by 2050. So we have now been living for about 2 years in a world where we have a firm commitment to bring those greenhouse gas emissions to zero. As part of those efforts, and more recently, the Climate Change Committee's 6th carbon budget saw especially the post-COVID recovery, as an opportunity to carry out the fundamental transformation of the UK electricity supply to become largely net zero carbon already by 2035. So to meet the national goal, the economy-wide target of getting net zero in 2050, the electricity system would need to do it a bit more quickly than the rest of the economy. A big part of the whole debate is, of course, the decarbonisation of heat and transport, which are the difficult bits of this whole low carbon agenda, and a lot of it is likely to come through electrification, which means that you need to accommodate additional electricity demand to supply those low carbon heat and transport demands. And at the end of last year, we've seen the UK government's 10-point plan, which puts forward a firm target of getting 40 gigawatts of offshore wind online by 2030, so in the next 9 years. And we'll refer to that based on our findings. And there's also been the latest version of National Grid's future energy scenarios that even propose net negative emissions in the 2030-2035 time horizon from the electricity sector in order to offset carbon emissions from other sectors which are seen as more difficult to decarbonize, so sectors such as aviation, shipping, agriculture, waste, and industry. What we've also seen happening over the past 5 to 10 years is some rapid reduction in the cost of offshore wind and other renewables and battery storage. So just as a very a brief reminder, if you go back to 2015 or so middle of the last decade, you would see CFD prices for offshore wind in the region of 120, even 150 pounds per megawatt hour, whereas the last year's CFD auction resulted in prices that are below 40 pounds per megawatt hour. So that all happens within a space of 5 years or just a bit more than that. So in that context, we've tried to come up with a white paper that provides quantitative evidence on how this net zero carbon electricity system should look like. So what sort of configuration in terms of generation and storage capacities we would need to get there at the least possible cost. And that has translated into 4 main specific questions that we will try to address, and which the following slides will try to answer in more detail. So the first one is, how much offshore wind capacity will GB need to meet its net zero target? Secondly, how much energy storage would be required to meet that net zero target? Thirdly, what other technologies beyond renewables and beyond energy storage could also take a prominent role in that net zero carbon system? And finally, what range of system costs and the unit costs of electricity we could expect across different scenarios to be prominent in that net zero system. One important aspect that we made sure we cover is to ensure that we accommodate and consider flexibility appropriately in our modeling. Flexibility has been shown to be quite critical for cost-efficient decarbonisation. A lot of our previous research has pointed to a quite substantial value of increased flexibility in the system to accommodate, in particular, variable renewables. So technologies like energy storage, demand-side response, enhanced interconnection capacity, or more flexible generation, they can all contribute to getting to that low carbon target more cost efficiently. And one of the key transformations we're also seeing is that while the energy flow would still be from large-scale, predominantly from large-scale generation through transmission and distribution grids, a lot of the flexibility that's required to operate those future systems is expected to come or to feed back from the customer side back into the electricity grids and to system operation. So the assets, the flexible assets at the consumer side, such as smartly charged electric vehicles, heat pumps, distributed energy storage, could all contribute to hitting that net zero carbon target more cost efficiently. Just a few words on the modeling approach. So what was the quantitative approach to developing those cost-efficient portfolios of generation and storage technologies? We've used our whole system cost optimization model called WESIM, which we subjected to net zero carbon constraint and security requirements, along with a host of other technical and economic considerations. In a nutshell, what the model does is it balances long-term investment decisions into generation, transmission, distribution, and storage assets against the short-term operation decisions. So it tries to find the best trade-off between investment cost and the operation cost, and to find the minimum overall system cost. You can see it takes a variety of inputs such as demand, generation, CO2 constraints, and as a result, it provides the optimal investment in various types of infrastructure, as well as the optimum utilization schedule of different assets. One important part of that model is that it uses what's called the representative distribution networks approach, where it's able to, in an aggregated way, quantify the cost of local distribution grids following a certain development pathway, so that the cost of that can be combined with the cost of the rest of the system. So, for instance, if you've got distributed sources of flexibility, such as DSR, electric vehicles, heat pumps, or distributed batteries, you could simultaneously capture the trade-offs between using those sources to provide support to the local grid, as well as providing support to the wider national system. So that's an important trade-off that we're trying to capture with this model between local and national objectives. I won't go through these tables in details, but this is a summary of the key assumptions we've made, and they're all available in the report. Maybe I'll just draw your attention to the assumptions on the LCOE, or the levelized cost of electricity of different technologies, because that will be one of the main drivers of the results we will see going forward. You can see that we've made an assumption that the offshore wind will be available at around £35 per megawatt hour going forward. Our central assumption for nuclear was that it will be the same as Hinkley Point C at around £92 per megawatt hour, and then onshore wind and solar would be available at around £50 per megawatt hour. All of these assumptions that we make also come with associated level of reliability, so the confidence level. Some of these assumptions are fairly robust, but some of the others, as you'll see later on, for example, the cost of the direct air capture technology, which is really not a mature technology at the moment, that's something that hasn't got a high confidence level, and we try to be quite transparent with it. Okay, I will now go through the four research questions one by one and outline the key findings. The first one is, how much offshore wind capacity will we need in GB to get to net zero electricity? So what the modeling suggests is that the capacity of offshore wind that we need to get there cost efficiently by 2035 is at least twice the existing 2030 target proposed by the government. So the target is to have 40 gigawatts of offshore wind in the system by 2030. And our modeling suggests that you should actually go for over 100 gigawatts of offshore wind to have the least cost net zero system. Now, 108 gigawatts is, of course, a lot of offshore wind capacity, and it represents roughly a 10 times increase from today's level of offshore wind. So obviously, it raises a lot of questions regarding the build rates, supply chains, etc. Because offshore wind, as we've seen, has a very favorable very favorable levelized cost of energy, we find that it dominates electricity supply in most of the cases we've looked at. So typically it provides over 75% of electricity supply in a year, even with some of the plausible cost variations that we used to test this. We found that solar PV at the cost that we assumed is not expected to play a major role in the UK system. So only if it cost drops very significantly, and we're talking about 2.5 times from our central assumption, is that we see that there is significant increase in the cost in the capacity of PV on the system. I should just make a little remark here that in all of these charts you will see the capacity mix on the left. So that's the cost optimal mix of generation and storage capacity. And on the right, you will see the same thing, but expressed as differences against the central case. So this helps us to identify how much more or less of capacity of a certain technology you see in a given case or in a given scenario. Okay. Obviously, such a high level of offshore wind, as I said, raises questions as to whether it's feasible to build so much in such a short space of time. So we might need to add more of the other technologies to make up for any shortfall, because, for instance, we are not able to build sufficient amount by 2035. So we've looked at what if we increase the capacity of PV and nuclear. Obviously, in that case, you need to build less offshore wind. But what we also find is that the system cost, the resulting system cost in that case, is about 3% higher. So that's not a huge amount, but because we're talking about system costs in the order of tens of billions of pounds per year, so 3% is still a fairly high amount. And also finally, we in most of the studies, we assumed that the GB electricity system will be net energy neutral, which means that any exports or imports happening over the interconnection over the year will need to balance each other out so that the net export or import would be zero. We have relaxed that assumption in one of the scenarios where we allowed the UK to build more than it needs for its own purposes and become a net exporter. And we find that, yes, it would make economic sense to build something like 18 gigawatts of extra offshore wind to support those net electricity exports. Now to the second question, that was about how much energy storage will we need in that net zero system. I've kind of deliberately skipped over the energy storage issues in the previous slide because it's discussed here in more detail. But what's quite obvious and probably even a little bit striking is that we need a substantial increase in the volume of energy storage to support a system which is dominated by wind and, to a smaller extent, solar energy. So the numbers we see here is that the battery storage that would need to be added to the system is somewhere around 140 gigawatts. It's a huge number, and that's about 100 times more than what we have today in the system. And again, it raises similar questions as for offshore wind. Can we deliver that much in that space of time, so in the next 15 years? The energy storage or the battery storage in this particular case is required in the system because it needs to help balance demand and supply. It also provides security of supply, so capacity margin adequacy, and it also mitigates the reinforcement of electricity grids. So your batteries, if they're placed in distribution networks, can help you to avoid overloading those networks and having to reinforce them. We've tested also what happens if you have a world where you have a very high uptake of demand-side response. Demand-side response is flexibility provided by customers, so by end-use technologies such as electric vehicles, smart heat pumps, smart appliances, which allow them to ship their demand in time. And we've seen that with high uptake of demand-side response, which corresponds to about 75% of the overall national potential being utilized, that does reduce the amount of storage capacity needed, but not by a huge amount. We've also tried varying storage durations. So the baseline assumption for the duration was 2 hours. So the ratio between energy and power of the battery storage was 2. And we try to vary that between 1 and 8 to see how that affects the optimal solution. And it seems that the modeling favors power over energy. So one hour duration batteries are a bit more attractive than 4-hour batteries. And finally, we also tested the role of long duration energy storage, or LDES, because of course there's a valid question whether we would need something of more long-term or seasonal character to help us bridge those maybe longer-term periods of low energy output. What we find is that yes, long duration could be a good idea, but we see that its cost needs to reduce to quite a low level of in what we find around £4 per kilowatt hour before it actually starts to get added to the cost-efficient portfolio. For all the higher cost points, it was not chosen by the model. Okay, and the third question was, what about other zero carbon or even negative carbon technologies? So here the two key points are about nuclear and DAC. So nuclear power would need to considerably reduce its cost, and again we use as our benchmark the cost of Hinkley Point C, which is about £92 per megawatt hour. So that cost would need to go down quite significantly, ideally halve, for it to warrant major new build of nuclear. So we see that at the cost of roughly half of Hinkley Point C, which is £45 per megawatt hour. The model suggests we should build 13 gigawatts of new nuclear. So nuclear should become a prominent component of that low carbon portfolio. And of course, there are developments in the nuclear industry where, through replication, there is effort to reduce those costs. So that's something that needs to be kept in mind. The second thing is about DAC, or direct air capture, so direct capture of carbon dioxide from air. We find that if that DAC is available at reasonable cost, it could be very useful to support low carbon heating, because it would allow you to ride through the cold spells, which would result in very high peak demand through purely electrified heat pumps. And if you substitute just a little bit of that demand by gas, that's offset through DAC, you could avoid a lot of reinforcement in your local distribution grid, and you could also avoid some of the requirements for battery storage to manage those high peak demands. However, we again need to mention that the cost of DAC is probably one of the least certain assumptions we have made in this white paper, so that needs to be taken with a fairly big pinch of salt. We also see that if the system is forced to go not just to net zero, but to net negative emissions, and we've tested a case with minus 50 grams per kilowatt hour, we see that we need a lot more DAC capacity to enable that. And because DAC is a net consumer of energy, we also need to build more offshore wind capacity, around 15 gigawatts, to supply that energy required for carbon removal. And that brings us finally to the fourth question, which is what happens to the cost? How would cost vary across different cases for this net zero system? An interesting headline is that in all cases we observe a noticeable reduction in total system cost from today's levels. So at the top here, you might see a dashed line, which is denoting our best estimate of the current cost of electricity, or system cost, which is around 10 pence per kilowatt hour. Now, of course, there's a lot of caveats as to how you estimate that cost, and of course, it's not the most reliable figure, but it's a useful benchmark. And also, I'll just mention that cost doesn't include any components such as metering, billing, tax, or supply margin. So that's just the cost of building and operating your electricity infrastructure, so your assets. So we've then expressed the total system cost across different cases as unit cost of electricity by dividing the total system cost and the total annual electricity demand, and then we've compared how those components change across different cases. What we find is that in our central case, that cost of electricity drops down to about 8.2 pence per kilowatt hour, and across all the other cases, some of them are below, some of them are above. The variation we find is between 7.8 and 8.8 pence per kilowatt hour. Again, with the caveats that the current cost is estimated, but it might be a bit different. I would also just say that the reason why we see the cost coming down from where we think it is today is, of course, we've made assumptions that the cost of renewables and the cost of battery will be a lot lower going forward than it was, let's say, 5 or 10 years ago. So it's a reduction from today's level. It's not a massive reduction, but we do assume that there'll be some further cost reductions going forward, and that's one of the reasons why the cost is being driven down. Okay, and I'll just now run through the key takeaways from this white paper and the analysis. Of course, much more detail is available in the report. So the report discusses things like annual output levels, the full breakdown of total system costs. It even discusses some of the hourly results to illustrate how the model or how the system operates during different system conditions. But to summarize on the key messages, we see that the offshore wind is set to become the backbone of the energy system in the UK. although there are also important roles for energy storage and other technologies. So first of all, we see that the capacity of offshore wind will need to at least double from the 2030 target to enable us to hit net zero electricity. If that becomes the problem because of build rates and other constraints, we might need to build more nuclear and solar PV. But that, of course, will result in higher system cost. We've kind of quantified it at 3%. We also see that we'll need a substantial increase in the volume of energy storage to support that highly renewable system. We've seen that direct air capture could be a very useful tool in the toolbox as far as it costs, materialize at the low level that we've assumed them. We've identified potential for GB to export a lot of its zero carbon electricity, so about 60 terawatt hours of energy annually. For nuclear energy, we see it could play a role, but with its costs coming down to at least a third, but ideally to 1/2 of the Hinkley Point C cost. And finally, with solar PV, because of the geography, we don't see that as being a major contributor to the low carbon electricity supply, unless we see a very rapid decrease in costs going forward. Okay, with that, I would wrap up. Thanks very much for the attention. I look forward to the discussion and the questions. Thank you.
Thank you very much, Marco. I'm very pleased to say we've been joined by two experts from the energy industry to form a panel alongside Marco and discuss some of the issues raised. Let me introduce our panelists. So first, Marta Koziewska, who is Deputy Director at Energy UK, responsible for the power sector. Energy UK is the trade association in Great Britain for the energy industry. She and her team focus on the challenges facing the country as it strives to decarbonise its energy industry in an efficient and cost-effective way while maintaining security of supply. Marta is a legal and policy expert with over a decade of experience in national and pan-European associations, energy companies and government ministries. And that includes time with National Grid Ventures, promoting building of interconnectors, and with LCOE, the European National Organisation for Transmission System Operators. Our second expert is Craig Lucas. He has over 25 years of experience in both industry and government, in senior roles in industry, but also in transport sector and telecom sector. He's an electrical engineer by profession and an expert on energy systems such as energy sector development, regulation and policy development, and management of research and innovation. He's especially interested in how new technology might transform the energy system, transform its business models, and interested in the customer experience in dealing with energy systems. He's presently with McDonald and is chair of the IET's Energy Policy Panel, and he was previously a director in UK government responsible for science and engineering in support of energy and climate change. So I will hand over now to Marta for some remarks.
Brilliant. Thank you very much, Tim, for this nice introduction, and thanks again for inviting me. I'm very pleased to be here. So before I kick off with my short remarks, just as Tim mentioned, I do represent Energy UK, so the trade association for the GB energy industry. And as Energy UK, we are very proud to be technology neutral, and actually to support the view that kind of in order to reach net zero, we need a varied and balanced generation mix, because that will help us both reducing the emissions and also maintaining the security of supply. I wanted to make this caveat because kind of that will explain all of the remarks I'm going to make. So first of all, I wanted to say big thanks and big congratulations to the whole team for producing the report, and it is an interesting one, and I encourage all of you to read it when you've got a second. However, probably what comes out quite naturally to me, that two things. So in the first place, a huge magnitude of the capacity needed, well, far beyond what we currently have, and even far beyond the government's ambitions outlined in various documents. And second of all, indeed, it's kind of very encouraging to see in this report various options for reducing overall the system costs. Every time I discuss net zero with my members, and in a quick chat we had before this session, we said that net zero is such a vast topic that probably we could be discussing it for weeks. But definitely the first question that I get from my members relates to how do we actually deliver all of this? And my kind of complementary remarks to everything that was presented in the report actually relates to what will be needed for the investors community to actually deliver on that cost-efficient generation mix as outlined in the report. And here I wanted to make 3 remarks. The first one is going to be pretty obvious and boring, but I still make it pretty much every single time. So having a stable and predictable policy framework will be absolutely crucial to deliver on that net zero ambition. A lot has been already happening. We kind of know the overall direction of travel. We've got the 10-point plan, we've got the energy white paper, we've got the 6th carbon budget. We know that the government will produce its net zero strategy close to COP, and that is all very, very welcome. But certainly a lot more needs to be done, and there are certainly areas where some further developments in order to provide that clear policy framework are needed. Just to give a few examples, for sure, heat policy, negative emissions, hydrogen, off the top of my head, are definitely those where some more work still needs to be done. So when talking about policy frameworks, the second aspect that I want to raise today is about market design. And I think that the Net Zero Challenge gives us a great opportunity to think about to which extent what we have delivered as a market design back in 2013 as part of EMR1 is still fit for purpose if actually we want to deliver on net zero. And that will be very challenging because kind of on one hand, we've had a lot of success with EMR1, in particular when it comes to offshore wind. And I strongly believe that contracts for difference will continue to be the main instrument to deliver that technology at the scale needed. At the same time, we need to think about other revenue streams for other technologies, and in particular for certain types of storage, in order to really kick that technology off. Last but not least, I think that in order to deliver all of this, another aspect that we need to look at is about governance and about institutions. It's probably fair to say, and I hope that many of you will agree, that what we currently have as governance and institutions is slightly outdated and not necessarily fit for the challenge ahead and for the challenge of the new system, which needs to be much more cooperative and where we need to look not only at electricity, but also at gas, at heat and transport, and just try to think about all of this together. So at the minimum, what we need a coordinated cross-sector planning. We need transmission and distribution to work closely together. And also we need more coordination and shared infrastructure in order to reduce consumer costs, as well as reduce the impacts on the environment and local communities. So perhaps I will finish by posing a question / request if actually going forward you could consider that aspect as part of your work. And indeed, it will be about what sort of policy frameworks will be necessary to give the best chance of that generation mix to pass.
Thank you very much. Marta, I'll hand over to Craig for some comments.
Thank you, Martin. Thank you, Tim. And I'm delighted to be part of this as well. I think it's a great piece of work. I guess I come at this from two perspectives. In my role in McDonald, we're working on pretty much every generation technology and, multiple countries around the world wrestling with this problem and increasingly working with energy infrastructure users of energy, trying to understand these issues. So I sort of bring some of that perspective to it, but also in my role in the IET as the policy panel chair, I've been very much part of looking at the future power system architecture and what needs to happen to enable a power system that achieves what's set out here. So my comments are in that kind of light, really, and some of them really echo Marta's, but I'll try and draw out a couple of some different strands. So firstly, on the analysis, I was struck as well by the magnitude of the capacity required and the scale of it. And to get offshore wind to that scale, we don't just need to sort out the constraints around network build, and those constraints are about things like landfall and the politics around landfall, but also the fact that it's starting to take off globally as a market, and we're now in a global supply chain, and we need to kind of understand what the enablers are to make those sorts of things happen without costs going in the wrong direction. The report opens some interesting questions for me about resilience, because I understand how least cost planning models work, but what technologies are we going to need to balance this system and operate it? And we've talked about being a much more flexible system, and therefore much more the operability of it is a big question, really, especially in a more electrified economy where people's need for electricity supply to be more reliable will only grow if that's the direction we take. And then the third comment is that I understand that this has not gone into a full multi-vector analysis around hydrogen, for example, but I do wonder whether the cost reduction around, say, electrolyzers or hydrogen or elements of that might change the equation in the time frame of the study, and whether you might end up, what difference would it make in terms of generation mix if hydrogen technologies became much cheaper and it became a viable round trip storage medium? So there's some questions there. And just to build on Marta's points as well, in terms of how to make this all real, I do think it'd be interesting for the authors to comment on what needs policy support and what do you think will just happen anyway, because the volume is there and cost reduction is there. I also think that in reality, many large energy consumers are voting with their feet now and trying to build their own generation or build their own storage, and whatever an economic planning model says, there are the sort of skewed incentives or direct incentives why they would be doing that. And I'd be interested in understanding what do you think, what would the least cost infrastructure look like if we just left the world as it is and people vote with their feet and kind of go off grid? I think it'd be an interesting question. And then finally, I really reinforce the point about needing a more holistic approach to this, because it's not just about the underlying economics, and you've demonstrated a world where electricity might theoretically get cheaper, which is counter to a lot of the discussion that we have about, greening the grid. But we're going to have to understand the value trade-offs between vectors. You alluded to that a bit with the direct air capture point, but the cross ISO interaction with gas, the need to understand how we actually operate a future electricity system, and what does it actually cost to do? I mean, you've got operations costs being fairly static, but it'd be interesting to explore that. And then I guess one final point, I was struck by your 75% of the DSR being deployed. What consumer experience is that going to represent, and how are the customers of this system going to engage with that if they're presented with that kind of reality, and how are we going to make that worth their while and unlock the value of that flexibility? So I'll probably ask more questions than we can cover in this webinar, but I think that just illustrates the richness of what's there. So thank you.
Indeed, thank you, Craig. Mark, I'm going to invite you to respond to some of those points. I think there are probably more than we can deal with in one quick session, but pick up a few of those if you would.
Yes, yeah, I'll try and cherry pick the ones the ones that are not too difficult. No, joke aside, I would say market design policy framework that will deliver this is a critical thing, and obviously that's not something that was within the scope of the white paper. It's a £1 billion question, really. What do we need to do to actually have the markets deliver those cost optimal outcomes. What I can say is that there are other parts of our IDLES program which look into more detail in terms of the market structures, the incentives, the mechanisms that you need to deliver a certain outcome. But that's definitely something we need to look at in more detail, because obviously the world we're proposing looks a lot different from the world we had 10 years ago, which was served well by the current market structure. So obviously some things will need to change, and I think Marta was very much correct in pointing out, for instance, the issue of revenues for energy storage. How will that come about? Because energy storage makes best commercial sense if it can access different revenue streams. So if you can provide multiple services at the same time, of course, within physical limits. So the question is, can it actually access all those revenues? So absolutely very relevant question. I'll touch briefly on the issue of resilience as well. So we did include some considerations of resilience in the white paper. In particular, we included a period of a few days of very cold weather to see whether our system can cope with, in particular, the increase in electrified heat demand. So a lot of these high capacities and high, in particular, high battery storage capacity is to an extent driven by those very cold, roughly 1 in 10 or 1 in 20 winters cold events. There are, of course, other aspects of resilience that we didn't cover and that we have on our agenda, and that will be things like having periods of prolonged low wind output, such as, let's say, 2, 4, or 8 weeks of very low wind output. Can the system ride through that if you've got a relatively low duration battery storage to support that? So that's something that we're very keen to look at going forward. Quickly on the hydrogen. Hydrogen is, of course, very, very topical, and we've already, since the analysis done for the white paper, we've already expanded the model to include explicitly hydrogen technology. So not just hydrogen generation, which is kind of represented in the model already as zero carbon generation, but this now can endogenously include investment in electrolyzers, in hydrogen storage, potentially even hydrogen imports if that's relevant. So obviously that allows you another dimension of flexibility, and I would, it's a pure guess, but if we had that other option available, the outcome might have looked different. I don't expect that hydrogen will become the main source of electricity supply, but there would probably be a lively and more dynamic interaction between renewables production of electricity and then converting that to hydrogen and using that, for instance, during low renewable output periods. And just a final one on the high DSR and the 75%. Yes, it's a very high uptake, and an honest answer from me is I don't know what sort of consumer experience that would entail and what would be needed to actually deliver that. What I can do, again, quite cheekily, is refer to another part of IDLES program, which looks in quite a lot of detail to consumer behavior, consumer experience, and consumer acceptance issues. But obviously, it's not just an economic issue. There's a lot of social, psychological, behavioral aspects to that. So that's, again, something that we assume that what if we have that? We try to see the implications of that, but how you actually deliver is another very complex research area. So I would stop here and leave some space for other questions as well. Thank you.
Okay. Okay, I'm going to pick up a couple of questions from the Q&A window and see where that takes us. So I think you've just touched on periods of low wind speed, Marco, and said a future piece of work is going to be looking at periods of several weeks. But can you just clarify what's the longest period of low wind speed in the present data set?
I think we currently have around a week of low-ish wind output, which a lot of people claim is not enough to have a full-scale resilience test. So we would try to increase that. But of course, it's always tricky to run an annual system model and include events that will happen only once in 10 or once in 20 years. So we will need to somehow probabilistically include that in the model optimization. But we are, I think we're on top of that.
Yeah, and sorry, that was Philip Pascal asking that. Keith McLean is asking about how do batteries help with seasonal storage and the need of that for heat. But perhaps you can touch on sort of longer term storage and storage versus fuels.
Yeah. No, so the batteries don't do much for seasonal, obviously, because they've only got a 2-hour assumed duration. Okay, we do have a lot of, so 140 gigawatts of batteries give you 280 gigawatt hours. So you can maybe do a little bit more than just 2 hours, but you can't really, at least not economically, move, let's say, a PV output from summer to winter. For that, you would need something different, something with long duration. And we've, as I've presented, we've tested the case where you have relatively low cost, low duration storage available. The model would build some of that, and that will help to balance those seasonal variations to an extent. But as I said, it needs to be really low cost. I always, give an example. If you have a battery that's 2 hours, that has 2 hour duration, it would roughly get charged and discharged every day. So you have, let's say, you extract value from those charge and discharge cycles on a daily basis. With seasonal storage, you have that happening on an annual basis. So essentially, you charge it a bit in the summer and then you discharge it in winter. So because you have, very simplistically speaking, one charge-discharge cycle in a year, that storage needs to be quite cheap for it to make economic sense. There's also the consideration of the cycle losses of that storage. If you waste 30-40% of energy in that also doesn't bode well for that technology. But again, that's something we would probably keep looking into, especially in collaboration with other people at Imperial who are much more experts on the technology side of things.
Okay. I might go back to Marta and to Craig for this discussion of hydrogen and other hydrogen-derived fuels such as ammonia, and for their views on how you see that, the role of those fuels within an electricity system, and then within the broader economy. Marta, what's your thinking on hydrogen and ammonia and so forth?
So I have to say, probably kind of hydrogen and in general, I would call it low carbon gases, definitely are going to have a role to play going forward. And kind of, as we have said, not only in terms of decarbonizing the power system, but kind of there will be useful definitely for those parts of the economy where more work needs to be done. As ever, and kind of at the risk of sounding like a broken radio, sort of having clear frameworks and clear business models for that to start will be absolutely crucial. We know that pretty much everyone is looking at the hydrogen at the moment, and it's just kind of a question of basically having a proper framework in order for people to start making it a real thing.
Yeah. Craig?
Yeah, a couple of comments. I mean, one is that the hydrogen and ammonia debate exists in a global market with the global value chains, and I think the way those value chains evolve and the way the costs fall will not be linear. If you get these large hub projects where there's a huge load of production located somewhere offshore, for example, and that can get to a particular price point, then that will move the dial in a particular region, and I think it'll be a kind of globalized market in the way that liquid fuels are. I think the other thing about the UK is obviously we do have a very well developed gas infrastructure, and the trade-offs between dismantling what we have and electrifying everything will look different to the way they do in other countries. So I'm not completely answering the question, but I think there's two uncertainties there. One is, how will the global market change? And I think we should not be too UK centric, and we should keep alive to that. And the other one is just keep thinking about what are the right infrastructure trade-offs overall.
Right. So Simon Anderson is asking an interesting question. It's sort of about scale. There's a lot of emphasis in our results on offshore wind, which is obviously a large-scale technology, and he's questioning whether this has been a bit slanted and what's the role for distributed energy, rooftop solar, field to grid, and so forth. So maybe I'll go to Craig first this time. Sorry, I'm coming straight back to you. About what's your take on the role of distributed resources versus large-scale resources?
Yeah, I sort of alluded to this in my comment. I think there will be scenarios where you can build distributed resources for very low levelized cost. If you're refitting a building and you can stick PV all over it with some very cheap technology. And I find that least cost models tend to underestimate how much PV turns up in real life because of those sorts of factors. And those people might not think they're participating in the energy market. They're just building something that derives value for them in a sort of bubble that they're in. So I think that is an interesting question maybe the way to access it from this is to think of some very low cost points and see what actually gets built. And of course, it then changes what storage you need and what the system operation costs are as well.
Martha.
No, I would kind of totally agree with everything that Craig said. That is also something that will play an important role going forward. I certainly don't have any data or any numbers actually to kind of counterbalance the analysis you've done, and in order to tell you how important that's going to be going forward. But yeah, certainly that is a space that we need to look at, and I kind of wouldn't underestimate the role it's going to play going forward.
Thanks. Marco, I'm going to do a version of this for you. So perhaps you could comment on why perhaps solar doesn't figure so strongly, because there's also a question about whether pitching it at £50 per megawatt hour in the central case was a sensible central case, or whether the lower cost option might have been more reflective. So why isn't a distributed technology like solar showing so much? And could you also comment on perhaps whether the storage you see as large, megawatt scale, grid scale storage, or garage wall type storage?
Yeah. Okay. With PV, yes, our settlement option was £50 per megawatt hour as its LCOE. The thing is, in the UK, probably the best annual utilization of PV you can have, and that's, we're talking about south of the country, would be roughly 11 to maybe 12% annually of capacity. If you go further north, then it gets even worse. The same amount of capacity in Greece or Spain would get you 25 or more percent utilization. At the same time, if you build a unit with capacity of offshore wind, you get well over 50, close to 60% utilization. So the economics of solar are just not that great in the UK, purely because of the natural resource. So the cost of the kit will need to get a lot lower than what we think is where we think it's going to make it feasible. And also, the thing with rooftop PV, it's never going to be as efficient as standalone PV applications. So then you sacrifice a bit more of the utilization, which again, in some applications, as Craig mentioned, will make perfect sense for the owners of buildings. But we don't see from the system point of view of that becoming a major contributor to the power supply balance. And then just to come to a second question, Tim, on energy storage, I think because a large part of the value of battery storage that we see comes from avoiding reinforcement in distribution grids, and a lot of that reinforcement is driven by electrification of heat and transport, and because that reinforcement happens at different voltage levels, so you have both low voltage scale, the street level reinforcement, as well as higher voltage, 33 kilovolts reinforcements. I would say that the right mix would probably need to cover both, very distributed and, maybe more centralized battery storage, so both kilowatt and megawatt type. There are, of course, cost considerations to be also taken into account, but I think probably a mix would be the right answer.
Okay. Mark, I'm going to ask you one clarification question that Rob Gross asked about LCOE. Do you work directly with LCOE, or do you break that up into capital cost and operating costs? And what about cost of finance? His point is that the low LCOEs come in part from low financing costs because of the very stable support mechanism.
Yeah, so we don't work directly with LCOEs. We convert them into capital costs, into the investment costs, and then we annualize that investment cost, making assumptions on the finance or let's say the interest rates or cost of capital. So that's the input into the model, and also the outturn LCOE. If you have some curtailment of renewables, the outturn LCOE will be higher than what you thought you were starting with. So yes, that's just a parameter which is useful to present, to compare different technologies, but it's more complex in the model.
Okay. I'm conscious we need to wrap up to finish on time. I'm going to go to Craig for a final word. You might want to relate the operability of a system such as this, and then I'll come to Marta in a moment.
Yes, I think I would just say that operability is not just about the duration, as you said. It's about how is a system with this amount of distributed assets on it going to work in real life and deal with things like black start and and so forth. And I wonder what the costs and challenges are around that. So I think that would be a really interesting line of inquiry to follow up from next. So yeah, but other than that, thank you for the opportunity to comment. I think it's been really interesting.
Thank you. Marta, some closing remarks from you.
Yes, I also wanted to thank you all for inviting me for that interesting discussion, and also for a lot of very interesting questions that I can see on the chat. What can I say? It is a big challenge. It is a big investment challenge. It is a big challenge in terms of how we are going to operate the system going forward. And my concluding remark would be probably about just let's get on with it rather than trying to get it perfect. We probably won't get it perfect, but kind of it is important to keep the momentum going, because basically, well, the time is running, and basically 2050 is not that far off.
Indeed, it's not. And you know, I might just pick up on that briefly. I mean, 2050 is not that far off, but 2035 is just around the corner. I find that quite startling to say that in 2035 we need more than twice the amount of offshore wind that government has in its 2030 target. That is an acceleration of building of wind, which is astonishing, and the build rate of storage that we see. And I acknowledge the lively debate in the Q&A about hydrogen versus battery storage and interseasonal storage. You know, a lot of interesting questions for us to take away and ponder on more. But however you look at this, either as fuel storage or electrochemical battery storage or something, a lot of storage to deploy. And thank you for your questions about you know, support mechanisms and market structures. I mean, that is good research material for some of our colleagues in the IDLES program who deal more in the energy economics and market design framework. So it's been a great experience for me as one of the authors and a leader of the project to see what questions this generates. We have, it's the classic researcher's final word, isn't it? The need is for more research, but genuinely, I hope we've made a contribution, but there are, as the Q&A demonstrates, an awful lot more detail to run to ground before we have anything approaching a finished system. So thank you, Marta and Craig, for agreeing to join the panel. Your input was very useful. Thank you very much, Marta, for presenting. Thank you to the audience for participating. I'm sorry that we won't have got around nearly, you know, anywhere close to all of the questions, and I know there were a couple of follow-ups to the answers. We'll go and ponder some of those, and we might be able to put a few words out, trying to tackle a couple of the questions we didn't get around to. So thank you all very much. Please go and download the full paper. There's a lot of detail in there, which I hope you'll find interesting also, and pass on to colleagues the YouTube recording when that becomes available shortly. So thank you very much, and goodbye.
Thank you.
Thank you.
Thanks, bye.